Okay. So 4 is cool. 5 is cool. Oh, so where is it? 4. 5, 6 are cool. Okay. And the last one is okay. Graphical what it means. You guys know graphical what it means. It's slope secant line, slope tangent line. Makes sense, right? Okay, cool. All right, that's easy. Um, then I sign 1, 2, 3. Then was just writing stuff down. So I don't think there's any questions about that. Or was there a question about 1b said? What about 1b? F prime x or y prime? On the first page of the 3-1 notes, all those different ways, where I wrote the phonetic ways like df, dx, dd of x. That's all. Yep, that's it. And then I did 2 and 3, right? Oh, 3 is too easy. I really did that one. Did I do 3? I did? Okay. And that was it, right? Okay, good. Number 3, the answer is just 3 because it's a line. So what's going to happen, we're going to talk about this. Whenever you have a line, the derivative of the line itself is the slope. Because if you draw a tangent to a line, guess what? The tangent is the line itself. If you want to go through the motions of the limit definition, which we should do, which is actually shown right here, there you go. You use the 4 definition. But the things that you still have an H that remains up top, and it cancels the 2 bottoms, just 3. Yeah, that's it. Yeah, that's all. Okay. Anything else? Nope. Okay. Let's get to the notes then. And see if there's anything else I have to pass back to anyone else in this room. No, everyone's got everything else back. Cool. All right, let's get the notes started. Just give me a sec here. Okay, we're doing notes. Let's go. All right, so let's go to, I think, this section B of 3-1. Yeah, here we go. So I'll talk about the relation between graphs of f and f prime. So we'll go through that. We'll see how it goes today. Talk about one-sided derivative. I do want to talk about the rules of differentiability. So some data table stuff. Not sure how far we can get. Yeah, we'll see how far we can get. This might be a little too ambitious. Okay. Okay. Relationships between the graphs of f and f prime. All right. So we have the explicit form for f of x, right? We can derive the form for f prime of x. We can do that, right? We did the limit definition. We do that. Great. Now we'll look at the graph of f of x along with the graph of its derivative f prime of x. Remember that for any point on the graph of f prime of x, the y value on the y value on the f prime graph is the slope value of the f of x graph, if that makes sense. So we use the graph of f of x to sketch graph of f prime of x. So here is what we're going to do. So this is f of x. What you want to do is find the slopes. Because this right here are going to be the y values on the f prime graph. So that's what we're going to do. We're going to try to find all these slopes on the original and make those the y values on the derivative graph. So if we look at points A, B, C, D, E, F, then what the heck, there's a G right here. The x values are the following: -4, -3, -2, 0, 2, 3, and 4. Okay. Now we're going to estimate the slopes. So sometimes it might be a good idea to get a ruler, but that's right. I'll just kind of sort of eyeball it a little bit. What do you think the slope looks like for a point A? About three. Yeah, I'd say about three. That's fair. Doesn't have to be spot on. What about the slope for point B? What would you say? Probably one. What would you say the slope would be at point C? And that's important because see how C is an extrema? It's actually a relative max because what's happening is that the slope, there's a transition, right? What was the slope right before I got to C? It was positive. What's going to be the slope after I pass C? What's going to be? Whenever you have that transition, that's always going to lead to an extrema. This will now help you determine, once you know the shortcut rules, because you don't want to keep doing the limit definition over and over. Once you know the shortcut rules, you can take any polynomial function and determine the true high and low points. Because the high points, low points happen when the slope of the tangent line is what? Zero. When you have horizontal tangents, you're totally going to have these transition points, these extrema. So, and where else is it going to be zero? What other point? E, totally 100%. Now, D is probably negative, right? Probably say negative one. At F, it's probably back to one again. And at G, I'd probably say maybe two. So what I'm doing is I'm just trying to estimate the slopes of the tangent lines at various points on the original graph. Now, once I have that, now I can graph my derivative. Now, anyone want to take a stab at what this derivative might look like? What do you think this is going to look like? It's quadratic, yes. And here's a good reason why. This crosses the x-axis three times. It has a end behavior goes down further to the left and up further to the right. So it's probably cubic. And we talked about this when we did the derivative of a cubic function. We got something that was squared. So it probably makes sense that this should be squared. So I'm going to do is I'm going to plot these points. I have to move my screen a little bit. So if I do that, -4, -3. So -4, 3. -3, 1. -2, 0. 0, -1. 2, 0. 3, 1. 4, 2. Okay, there we go. So what can you say about the y values of the graph f prime when the y values of f are increasing? Well, obviously f prime is positive. On the f graph. So for example, my f graph looked like this, right? And this portion right here, are the y values increasing on this is I just replicated the f graph. That's no hiding. On this portion right here, the y values are increasing. What's meant by that is as x increases, or as we go from left to right, what's happening to the graph? Is it rising or falling? So now if you look over here on the prime graph, are all these y values on that prime graph above the x-axis? They are. When the y values on that prime graph are above the x-axis, it means that the original graph is increasing. Because if you have positive prime values, you're going to have increasing values of y on the f graph. So what can you say about the y values of f prime? They're positive. That's what we could say. So vice versa, if you're going down, they're negative. So, and I think when we do some curve sketching, when we do this little demonstration, it's on GeoGebra. This will help you understand better why this is happening. So let's look at it again. Let's look at another one here. Here we got piecewise graph, clearly. We got several segments. We have some segments that are going down, up, flat, down, up, right. So if I'm going from -infinity to -4, we're supposed to look like this. So if you look at this first interval, from -infinity to -4, are we thinking like a roller coaster, board roller coaster here? Now the ride starts. Are you going down or up? Then you hit the low point, then you'd be going up, then flat, then I lost it. Then down, then back up. Yeah. So, but let's estimate that. And we can't estimate because these are all just segments. So I'd probably say the first one, -1, maybe. You're gonna say -2? Okay, I'll go with you. I'll say -2. How about from -4 to -2? And a -2 to 2? Yeah, so that's probably zero slope. That's one slope. -2 slope. Next slope, -3. Ah, come on. -4. Yeah, you're probably right. And the next one's probably what? 3. So now what you're gonna do is you're gonna graph it like this. And by the way, these are open intervals, mind you. These are open intervals. I'm gonna draw it like this. Let's see. Don't rush it. Take your time. Okay. Let's talk about it. So these are all a bunch of flat lines, right? Because what am I graphing? I'm graphing the derivative. And each of these derivative values are just a certain number. Like for this portion right here, the middle portion, what's the derivative value from -2 to 2? So when I graph on the derivative graph, I'm just going to graph y equals 0. Y equals 0, yes, -4. That's 3 and so forth. However, why do you think I'm doing a bunch of circles? Like why not, like, why not build? Like why are there open circles? We're doing open intervals here for sure. That's good reason. The other thing too is we'll talk about later today is that when you have these sharp corners, they're not differentiable at sharp corners. The reason why is because we are kind of torn, right? Like for example, this corner here. What's the slope of this corner here? Like, I mean, is it part of this line or is it part of that line? It's kind of ambiguous, right? I'm not really sure what's happening there. We're going to talk about left and right-hand derivatives, and we use limits, just like we did for left and right-hand limits. Once we get that discussion later today, it'll make more sense why you don't want to include them. But for now, because we see open intervals, let's just respect that, and let's keep them open over here. In fact, actually, the College Board, they tell you to use open intervals, just so people are not confused. Because it is kind of unclear, like at 4, which intervals it really belong with, right? It's not quite clear. So we use open intervals to show that. Does that graph make sense for f prime? And what can you say about the y values of the graph f prime when the y values are decreasing? Well, f prime's negative, just so we saw up above. And what can you say about f prime graphs when it has a horizontal tangent? Oh, great. I'd move that. There we go. There we go. It's gonna be 0. Right? When you have horizontal tangents, you have prime 0. So hopefully that's okay. Any questions? We're good? Cool. Okay, let's talk about one-side derivatives because we do need to have that discussion. Let's look at this piecewise graph. We'll do another sketch, and then we'll do this little demonstration. I might skip this table for now. I don't know if I want to do that table today. We'll see. Let's have a discussion about one-side derivatives because that's a good discussion to have right now. Okay, so recall, for a given function, or for the limit as x approaches a to exist, both the limit as x approaches a from the left and the limit as x approaches a from the right must have the same value, right, for a limit to exist. Since finding the derivative involves finding a limit, let's replace x approaches a with a derivative point a with the limit as x approaches a with the left-hand derivative and the limit as x approaches a positive with the right-hand derivative. So for a given function, in order for the derivative to exist, both the left hand derivative and the right hand derivative. So we'll use LHD and RHD. So how does this look? It looks like this. The limit as x approaches a from the right of f of x minus f of a over x minus a, or another we could write too is like this. Do it again. So I'm giving you guys a lot of information right now. But do you guys see why these would make sense?
When would you use that?
The A one's called the alternative definition. That's just if you're using like you're looking at the 2 points at x and a on the x-axis. This is if you're looking at x and x plus h. It's the same thing. But if you think about it, if you're approaching 0 from the left side, x plus h is less than x. If you're approaching h from the right side, x plus h is more than x. So here, if you're approaching a from the right side, then x is a little bit bigger than this, right? Approaching x from the left side, x is a little less than it. So that's why we see that. So let's do some practice for example 6. So for example 6, you're asked to show a function that does not have a derivative. The first thing you always want to do, and I know we haven't had this discussion yet, we'll do this more tomorrow when we get more into the theory of derivatives. But first thing, should always check for continuity. Check for continuity. Well, we'll do it really fast. What's f of 1? 2? What's your left-hand limit? Right-hand limit? Okay, good. And f of 1 equals limit as x approaches 1 of f of x. To both 2. Okay, cool. So the next thing we need to do, if I do a sketch, I mean, it should seem pretty obvious. I don't know if it's too obvious, but if I plug in 1, I get 2. That's a whole. Plug in 2, I get 8. Oh, you're right. Darn it. Yes, you are correct. Thank you. So much better. Here we go. And of course, it links up over here. And the slope is 5. Now, I'll tell you for certain, this is the derivative won't exist. But here's what we're going to do. For the left-hand derivative, you want to take the limit as x approaches 1 from the left side of f of x minus f of 1 all over x minus 1. Well, if I'm approaching one from the left side, right? If you think about it, um, well, first of all, what's f1? 2, right? And which expression am I going to use if I'm approaching one from the left side? If I'm going to use the top one or bottom one? Good. Yeah, because x is less than 1. So I write as 2x squared, and the bottom is x minus 1. So I can factor out 2, and continue breaking it down. Fortunately, things cancel. What cancels? Plug in 1, you should get 2. Okay, that's my left-hand derivative.
Did you get 4?
Oh, shoot, you're right. Sorry, my apologies. Because I can't multiply. Good. You are correct. It is 4. I did check. I was trying to check the shortcut rules, and yes, you are correct. Okay, now next up, let's try it again for the right-hand derivative. Now, if you do right-hand derivative, I'm doing the limit as x approaches 1 from the right. Okay. So now which expression we use now? If x is bigger than 1. Slightly bigger. The bottom. Good. Yep. So we have 5x minus 3. F1 is still 2 over x minus 1. The shortcut rules will be so much better once we learn it.
When do we learn it?
Thursday. What goes away? So you get 5. Because the LHD does not equal to RHD, we do not have a derivative. And that's how you prove it. And it's kind of weird. It's kind of hard to tell, but there's actually a sharp corner. It's really hard to tell if the slopes are pretty much the same, but so this tells me if like absolute value, for example, right? Absolute values always have sharp corners at the vertex. You're never differentiable at the vertex of absolute value. Because if you think about absolute values, isn't absolute value a piecewise function, right? And doesn't absolute value have 2 different slopes on each side? And now we're starting to see, like for example, look at 5x minus 3. The derivative of that was 5. That happens to be the slope of the line. So we're starting to hopefully make a little more sense of how these derivatives are coming about, right? We're looking at slopes of tangent lines, and of course, if you have a line itself, the tangent line to the line is the slope. That looks good.
Why would you the formula to find the left and right hand derivatives? Like, isn't the
No, I'm using the tangent formula. This is the limit.
is the tangent formula the like the x plus a?
Y-
Not the.
Yeah, it's the same thing, but I do a limit instead.
But I thought the f of x minus f of a over x minus a is for finding
The
the
secant.
Yeah.
Exactly. And then I just do a slight adjustment to put the limit in front to make it a tangent line.
Oh,
Yeah. Yeah. I can check your notes to make sure you got it right. But yeah, that's just adding the limit. So that's what's going on with one side derivatives. Um, let's look at a graph situation again. And instead of doing the table, I do want to do this little demonstration on GeoGebra. because it's kind of fun to do. All right, so here we got f prime graph. Okay, so here the derivative is -1. Here the derivative is 2. So what this tells me is that f prime equals -1 when we're going from -infinity to 1. F prime equals 2 when going from 1 to infinity. Okay, now 0 comma 0. Now 0 comma 0, well, when x is 0, which interval does it fall into? First or second interval? Yes, the first. And the slope is -1. And when did we start seeing a shift? It will slope afterwards. Now we have to make this continuous for all of x, which I did. So check. I had to make sure f of 0 is 0. Check. I had to make sure use the derivative values. Check. So there we go. That's a sketch graph. So this is going the reverse. I gave you the derivative graph. I wanted the original graph. But what I did was I first located 0 comma 0 and drew the slope that it belonged to. 0 comma 0 belonged to that first derivative, -1, the one from -infinity to 1 for that interval. Then I did the other one after that. Now, this format kind of sucks, actually. I don't really like how it's formatted. I should have fixed this. So let's try this now. This is kind of a fun, you guys can just relax a little bit. Let's go to Schoology. Here we go. So under derivatives, I think I'm under a test review. There's nothing there. Under, no, it's somewhere here. Homework quizzes. Ah, there we go. Homework quizzes. Okay, cool. Yes, because we do have homework quiz. So GeoGebra practice. Here we go. This is gonna be fun. All righty. I'm gonna reset this. Okay, so the black curve is the original. Okay. So we'll call this f of x. Now the one that has the dots is going to be the derivative graph. Now there used to be another one. Actually, it was, I think it was the U.S. Navy had an interesting one. It's not active anymore, but it actually was a freehand. This is not freehand. What I have to do is I have to move these dots up and down, and I'm moving these dots to to wherever I feel the slope is at all these various points. So on f of x at -6. See, look over here. This slope is probably negative, right? Would you say over here? Mm-hmm. And if I were to kind of I know I'm kind of cheating a little bit, but if I were to kind of like estimate, probably it's a 1/2 slope, let's say, -1/2. Mm-hmm. Yeah, if I says -1/2. So I've kind of got a good spot right now. Okay, at -5, it looks like it's probably steeper, probably more like -1. So I'll probably do that. At -4, it's probably still about the same, maybe a tad steeper, so maybe like that. At -3, it's probably more like -1 or probably a little less. At -2, it's maybe it's negative, right? -2, but it's kind of shallow, probably like -1/2. Then is it positive at -1? Yeah, and definitely crosses 0 over here, but very shallow again. At -2, it's probably a slope of 1. At one's probably still slope of about one, I think is fair. At two, it's probably more like a slope of one half, I'd say. It's getting less steep. At three is probably a slope of zero, or pretty close to. It's still slightly positive. At four, it's definitely more of a negative slope, probably negative one. At five, it's probably going to be negative two, let's say, maybe. And at six, probably the same thing. Okay, let's see how I did. I should do better than that. That's crap. Okay, well, I think someone could probably beat me. Okay, I think I might. Anyone think they get better than 86%? You don't want to try? You can come up here and do it. You guys can help her out. You try. Okay. Okay. Well, you guys are gonna help him out. Oh, so I'll get chicken nuggets for you guys.
You get higher than you? Huh? You get higher than you right now?
If you could beat me, let's see if you beat me.
Walk in, bro.
Okay, I'm right here, walk in.
Well, you guys have to help me.
That's probably like one third. Or negative.
Negative, like right here ish. A little up.
You can always adjust. You don't want to. It's not like you locked in. Like
All right.
It's all you hit check accuracy.
Well, I feel like this is a little bit shallower than that. Maybe at -5. Just a little.
Maybe put six down a little bit lower.
Yeah. Like that. Up. Okay. -4 is a little positive.
And never been access this, by the way, so you can use this to practice for the quiz.
Wait, is it like right
There's a quiz?
Hmm?
This is a quiz? Like we're gonna get this?
I'll give you a question where I'll ask you to sketch through.
Oh, okay.
Some say you could use this to help you.
Is that that's a
Right below one. Right below one.
right there?
That's below one.
2,
That's the
I
one.
think
One.
almost exactly. A little bit higher.
I say it's like that. -1,
Definitely 5.
1. This it's a little shallower. If it's like this, I feel like this should be more curved.
Yeah, I agree.
This is either higher or these two are
I
lower.
think that was higher. You think that
This is a little low. Yeah, a little low.
Like this.
Yeah, it looks smooth. See, mine wasn't as smooth actually, so that's kind of my fault. I should make. You want? Yes. Do you want to look?
Okay.
Smooth? I would
Okay,
agree with
zero.
that.
Well, let's see what 1 would be. One's like it's like this.
Yeah, right there.
Okay, cool, good.
2
Just negative.
right there.
Right there.
We'll go right there. 3.
That's under one, yeah.
Love it very much.
4. 4 is about 1.
I was supposed to watch the Super Bowl yesterday, so
I think it's a little bit more like this.
Yeah, yeah.
5. Shallowing out. Kind of like that, right?
The higher.
6 or 0.
6 is almost.
Yeah,
it's good. So I think it's close to 0.
Going 0.
Oh, dude, I think you get like 98%. Check accuracy.
Yeah.
26.
You got 10% higher.
Okay.
Wow,
Congratulations, you did
that was almost perfect.
All right, I'll get some Chick-fil-A for you guys.
It was that negative.
Maybe tomorrow. Not tomorrow. I see you guys
Negative 3.
Wednesday and then Thursday.
Yeah,
breakfast.
Did they have breakfast?
The breakfast.
Is it good? How's the breakfast? Chicken, we have chicken biscuits or something? All right. All right. Okay, cool. Well, so hopefully you guys see what's happening there, right? It's a really cool exercise. I like it a lot. So it does slow down your computer a tad, just keep that in mind. So cool. Good. Excellent. Good. So that's what's happening there with derivative sketches.
like graph.
One will be just there's a function, find me the derivative of the function using the limit definition, and one will just be just sketching the derivative from a graph. Yeah. Um, I think let's skip this part for now. I want to go jump to differentiability. Just since we had this discussion, do you want to have that talk for a little bit and talk about ways things are not differentiable? And then we could we get to example one, cool. I don't know if we get to example two yet. Ooh, if you guys will totally hate me to do example two using the limit definition. Yeah, let's see how far we get. So let's go over here on 3.2. Okay. So 3.2, differentiability. So differentiability means the ability to take the derivative. Can we take the derivative, right? And in example 6 of section 3.1 notes, we compute the left right-hand derivatives to determine whether the piecewise function was differential x equals 1, right? We saw the left-hand derivative was 4, right-hand derivative was 5. This means the following. If we create a tangent line from a secant line where the second point was to the left of x equals 1, the tangent line was 4. If we create a tangent line, um, yeah, so here's what it's trying to say here. Let me draw it. It's the wording's a little confusing. The graph looked like this, right? So you're trying to do this. So for your left-hand derivative, if you're going to the left of x equals 1, here's 1, right? Here's 1. You go a little bit to the left of it, and that's 1 minus. If I draw a tangent line, or sorry, draw a secant line, if I try to draw a secant line, it's pretty close to 4, right? Pretty close to 4. Now if I do this, going from the right side, I mean, obviously it's going to coincide the blue line. Well, that's slopey. 5, right? So since we create two different tangent lines, depending on which side we start the secant line, we don't get a unique tangent line. Therefore, we're not differentiable at x equals 1. Essentially, these are not the same. They don't equal each other, right? That's a problem. The left-hand derivative does not equal the right-hand derivative. So there are ways we could classify this. Any discontinuity corners, and what's happening here, if you're not continuous, you're not differentiable. Because if you think about it, if I try drawing a left-hand derivative, I'd be doing something kind of like this, right? That'd be like almost like a vertical slope in a way. Obviously, if I draw my right-hand derivative, it looks like this. So when you're not continuous, you're not differentiable. Which means you need to have differentiability to be continuous. We'll have that discussion, more of that discussion tomorrow. But you need differentiability, you need continuity for differentiability to happen. Here, what happens is the left-hand derivative does not equal the right-hand derivative. Both are finite values. Just like we saw in that one example where the left-hand derivative is 4, right-hand derivative is 5. So we have a corner. Corner happens when the left-hand derivative and right-hand derivative are not the same, but they're both finite values. Like maybe one side's 2, the other side's 3. One's like -2, one's like -5. I don't know. Like there's always different things that could happen. That would be true for a corner.
What if it's a perfect V?
Doesn't matter
So
because it's still a corner. I mean, but what do you mean by perfect V? Oh, like the absolute value, same thing. It's the same issue. Like absolute value, right?
Yeah.
Because piecewise, once like let's say if like absolute value of x, the left side's negative x, right side's positive x. Slope -1, slope +1. They're very different. And these are two more. A cusp looks like this. And a vertical tangent looks like this. So what happens here, my tangent lines, the left-hand derivative is -infinity. The right-hand derivative is +infinity. Or vice versa. Because it could also look like this too. So what's happening is that we'll call this A. I'll call this A over here. What's happening is that as you're approaching A from the left side, you see how that tangent line is getting more and more vertical. So this first red line, if I get closer and closer to A, when I get down to here, that's a very vertical line. Or slopes of vertical lines. Undefined, we don't know, right? Because you have all this change in Y, but no change in X. Likewise, if you're approaching A from the right side, the same thing. That's going to have a vertical slope. But what happens more specifically for a cusp is the left-hand derivative and right-hand derivative are both approaching infinity, but different signs. One's negative, one's positive. Or it could be vice versa. Like in this case, that could be positive infinity, and that could be negative infinity. As I'm getting closer and closer to A here, on the left side, that orange line is going to get closer to positive infinity. On the right side of it, the orange line is getting closer to negative infinity. So that's what gives rise to a cusp when that happens. For a vertical tangent, what's going to happen is something like this. As I'm looking at each side here, as x approaches A, actually, I'll just write left and right-hand derivatives, but he's that way. The left and right-hand derivatives equal each other with positive infinity or negative infinity. That's what's happening. So they both equal each other, but they're both positive or negative infinity. Anyone want to take a stab? What kind of equation would follow example 4? I might remember this. Q of x does that. Q of x looks like this. When we do the shortcut rules, it'll make so much sense. you'll see why that would provide such a tangent line. Cusp, you guys probably don't know this, but I think that y equals x to 2/3 power. I think it looks like this, if I'm not mistaken. I think that would be so you could get like the cube of x squared. But the one that we did where the left-hand derivatives were 4 and 5, what example is that called? That's a corner, correct. So notice that in case one, the function is not different. Now, so anyway, before I get to this discussion, actually, I will be talking about differentiable and continuity. First off, any questions on these classifications? And we're going to do more of this. Don't worry. Once we get to the shortcut rules, we will classify. Because to have you do the limit definition of this, you are going to really be upset at me. Or this one too. Those are not fun. But the shortcut rules make it more manageable. So I'll wait till we do that. But just like how we had different ways of discontinuities, you have different ways of lacking of differentiability, if that makes sense. So something to keep in mind. But I did say earlier that you do need continuity for differentiability to happen. So if a function is not different, sorry, when you're not continuous, so you know this happened, right? If you're not continuous, you're not differentiable. So if you're differentiable, you're continuous. Are you guys familiar with something called contrapositive statements? Do you guys ever do that in Ms. York's class?
So like a square root rectangle.
Yeah, kind of like that. Yeah, it's kind of like it's kind of like that. So, for example, Lucas, what city do you live in? What city do you live in?
I didn't know where you
What
said-
city do you live in?
Oh.
Okay, good. What county are you in?
Then
Santa Clara. Okay, Santa Clara. Okay, good, great. So we could say, if you live in Palo Alto, are you a Santa Clara County resident? Yes, you are. Okay. If you're not in Santa Clara County, then you're not in Palo Alto. That's true too. So that's a true statement. But if I were to say, um, if you don't live in Palo Alto, you're not a Santa Clara County resident. Well, you could live in San Jose, you could live in Santa Clara, you could live in Mountain View, right? Or if you're to say, if you just reverse it, if you're a Santa Clara County resident, do you guarantee you live in Palo Alto? No, right? So it's kind of like, so here's the thing is that these contrapositive statements, which you might remember back in the day, if A leads to B, then negative B leads to negative A. That's what's meant by contrapositive statements. They're always logically equivalent. I'll give you another example. If you were to say, if you're in my calculus class, you are a Sacred Heart student. True, right? But if you're a Sacred Heart student, are you in my calculus class or pre-calculus class? No, like there's people across the hall, right? Or if I would just negate it, if you're not in my pre-calculus class, you're not a Sacred Heart student. That's not true either. But if I reversed and negated and said, if you're not a Sacred Heart student, then you're not in my pre-calculus class. Like those kids at Menlo, they're not Sacred Heart students, they're not in my pre-calculus class, right? So that's what's happening here. We saw that if you're not continuous, you're not differentiable. So it means if you're differentiable, you are continuous. So if a function to be differentiable by a point, it must be continuous at that point. And all these cases show the function is continuous x equals a, but it's not differentiable for cases 2, 3, and 4, for the corner, the cusp, and the vertical tangent. So what does this imply? If a function is continuous at a point, it may or may not be differentiable at the point. So continuity does not guarantee differentiability. Just because you're continuous doesn't mean you're necessarily differentiable. You do need um, continuity to be differentiable, though. So the differentiable does guarantee continuity, but not the other way around, just so you know. So very, very important. So whenever you're asked to find if something's differentiable, the first thing you should always do, check for continuity. If you're continuous, cool, but still we have to dig a little deeper. But continuity is necessary for differentiable to happen. So this will be our last example for today. I'm not going to do example 2 because I want to do that when we do shortcut rules. So consider the piecewise function. Determine if it's differentiable. Okay. So first of all, check for continuity. You want to check for continuity. So f negative 1 is going to equal 1. The left-hand limit is going to be 0. The right-hand limit is going to be 1. So actually, the limit does not exist, right? So you're not differentiable. Because I just plugged in negative 1 to both the left and right sides. I should have done it more formally, run the notation, but if you plug negative 1 to the top, negative 1 to the bottom, forget, but they don't link up. So it's not going to be continuous. It just can't happen. So therefore, you're not differentiable. You can't have that either. Example 2, you could probably just graph it and see for yourself, but analytically, that's just kind of not fun to do using the limit definition. So I'd rather wait to do that one using the shortcut rules. Example 3, we'll have to do piecewise functions. We're going to do a lot of stuff in the calculator as well. So make sure you have a calculator. Make sure you do the derivative in the calculator. There's also an IVT for derivatives. We're going to talk about that as well. So we're going to get heavy into theory, just, tomorrow. Not tomorrow, sorry. Wednesday. And on Thursday, our last day before break, I will go over the shortcut rules with you guys. So you guys will know all the shortcut rules.
The quiz on Thursday also have shortcut rules involved. It's
No.
just the graphing.
Graphing, and you have to do the limit definition. Yeah. So it'll be good. And then when we come back from break, just, we'll start talking about application derivative, like using physics applications, like linear motion, if those are in physics. We'll do that. We'll do like other kinds of techniques. And we do have a test coming up during the first week of March. So, but we're humming along just nicely. Yeah.
The definition of limit to just mean like.
The limit to LM, H approaches 0.
H approaches 0.
And you have to do all the analytical stuff, right? Yeah. Correct. Correct.
F of x
Hmm?
over h.
Yep.
Okay.
Homework. What do I want to do for homework for you guys? Kind of like 4, 5, 6 of handout B. And I might do example. Yeah, I might do like number 3 and 4, 5, 6. Yeah. Yeah, I think I'll do 4, 5, 6
An 8 count in about 45 minutes.
and 3, 4, 5, 6. Yeah, that's most likely what I'm gonna do. I'll put up in school terms. So it'll be 7 questions.
Yeah, of course. Sorry, I think